Let's take a look now at the finite geometric series, which is going to help us get ready for generating functions. I'm going to start by talking about what a geometric series is. So before we even look at what I have written out here, a geometric series is a series where I get from one value to the next by multiplying by some common ratio. So if I start with 1 and I multiply that by 2, I get 2. And I multiply that by 2, I get 4. Multiply that by 2, I get 8. Multiply that by 2, I get 16, etc. So this is the same series that I have written here, 1 plus 2 squared, which is 4, plus 2 to the third, which is 8, and so on. And it is in fact a geometric series, again, because I multiplied by 2 to get to the next value in the series. Now, what I want to do is take a look at how we might generalize if I have a finite meaning there's only so many values in the series. So in the past video, when we looked at the power series, remember the upper limit was always infinity. That is not the case right now. So how do I model the summation as k goes from 0 to n of 2 to the n? I model it as 2 to the n plus 1 minus 1. How do I model that for 3 to the n? Well, it's going to give me 3 to the n plus 1 minus 1 over 2. And then again for 4 to the n, I've got 4 to the n plus 1 minus 1 divided by 3. So my question is, can we have some sort of general solution based on whatever the base is of our geometric series? So 2, 3, 4, and so on. And it appears that I can write this as the summation as k goes from 0 to n of x to the n as x to the n plus 1 minus 1, and then I'm going to divide it by x minus 1. That appears to be the pattern that I see, because as you can see, this value is 3, but this value is 2, so I'm subtracting 1. This value is 4, but this value is 3. This value is 2, but I divided by 1, which was 1 less than that. So this is my conjecture for how I can write the basic finite geometric series. So again, what we have just discovered is this formula based on what we know. Now what I'm going to do now is I'm going to multiply by -1 on top and on bottom. And I'm going to do that just so that this denominator is in that same format as what we're used to with the fundamental identity. So if I multiply this by -1, that gives me negative x to the n plus 1. It gives me positive 1 here. It gives me negative x here and plus 1 here. And again, cleaned up, this is what it looks like. So again, this is a series that has an upper bound of n. So previously, before this time, when we looked at the fundamental identity, we always looked at an infinite series, but when we're looking at this specific series, the finite geometric series, we do have an upper bound. We're going to revisit the linear equation model question we first looked at when we were just looking at how to model with generating functions in video 8.4.1. So at that point, we stopped right here. We said, okay, we were able to model that the first variable was from 0 to 10. The second started at 12 and went on to infinity, so it's not necessary to put the 28 there. And the third and fourth variable both stopped at 9, so went from 1 to 9, notice not 0 to 9. So this one's going to be a tricky one. There's going to be a lot going on. So I'll try to keep it as organized as possible as we move through this. So for g of x, I'm going to first look at x sub 1, so the first variable. The first variable starts at 0 and goes up to 10. So because there is a specific upper bound, I'm going to be looking at the finite geometric series, which as you can see, is the summation as k goes from 0 to n of x to the n, and we can rewrite it as 1 minus x to the n plus 1 over 1 minus x. Now it's up to you if you want to write it in this format first as the summation. I don't like to do it that way, but if you did, again, you would say that's from 0 to 10 because this top value is 10 of x to the n, and that would help you to know that n is 10. So I'm going to rewrite that first expression that represents x1 as 1 minus x to the 10 plus 1, or 11, divided by 1 minus x. For my second expression, notice this is not an upper bound question. It's not a finite series. There's no end point, so I can actually use the fundamental identity. So what I have here is I have x to the 12th, x to the 13th. We're going to use that strategy that says factor out an x to the 12th, and then you have x to the 0 plus x to the 1st plus x squared on to infinity. And we'll come back to that on our next step, because we're just going to do one step at a time. And then for our third and fourth value, before I can write it as a finite series, I need to think about the fact that the first value is x to the 1st and not x to the 0. So what I need to do is I need to factor out an x from this series, but I also, because there's two of them, I'm basically taking x times x to the 0 plus x to the 1 plus x squared, and then times that exact thing again, x times x to the 0 times x to the 1. So again, because it's squared, that's why we have two of them. So essentially I have two x's out here, and then I have x to the 0 plus x to the 1st plus x to the 3rd, all the way up to x to the, remember it used to go to 9, but I just took an x out, so it actually goes to 8 now, and that's quantity squared. So this is where we are so far. Again, this is a product. And so what I have to represent x1 is actually perfect just the way it is. So for g of x, this stays 1 minus x to the 11th divided by 1 minus x. For that middle value, I have x to the 12th, and then I have x to the 0 plus x to the 1st. Hopefully you recognize this is the fundamental identity, which means I can rewrite it as 1 over 1 minus x. So instead of 1 over 1 minus x, I'm going to write it as x to the 12th over 1 minus x. So I'm writing all of that together. Now, what I have left over is this x squared, and this portion here, which is back to the finite geometric sequence. So again, finite because we had that upper bound that started at 9 but is now 8 since I factored out an x. So that is going to turn into 1 minus x. N is now 8, but it says n plus 1, so that's 1 minus x to the 9th, and then over 1 minus x. And now all I want to do is just, oh, I'm sorry, n squared, because there's two of them. Now I've already squared the 2 out here, so I don't have to worry about squaring it again. I've already taken that x squared out. So what's my final solution? Well, my final solution is that I actually have x to the 12th, and then I have x squared here. So if you want, you can take that x to the 14th out front, and later on that might be helpful to do. So I'm going to go ahead and do it now. And then I'm left with 1 minus x to the 11th over 1 minus x. That middle term is now 1 over 1 minus x, and the final term is 1 minus x to the 9th over 1 minus x, quantity squared. And that's where we're going to stop. Coming up next, we have our last Readiness for Gen Fun video, which deals with the binomial and extended binomial theorem. After that, we get to actually work with generating functions.